All right. So good afternoon once again. So in today's lesson, we are going to begin by discussing a couple of concepts. But first, I want to give a general overview of what we've been looking at so far. These are the next few things that I'm going to be talking about are very important concepts relating to the topic that we've been looking at, operating systems, for the past few weeks. We started off by defining what an operating system is. We said it's basically a set of software that controls and coordinates all the activities of a computer. Now, to drive that message home, I'm going to basically just give you a summary diagram that hopefully will help make things make much more sense. So this is how you want to take a look at it. Our entire module is based on computers. The computer, we said, is broken into two parts. You have the hardware and the software. In the first part of the lesson, we've been focused on the computer hardware. The second part, the second four topics, we've been focused on software. Now, software is divided into two categories. You have what we call system software. System here meaning the computer system. So system software means computer system software, also known as the operating system. So these two words mean the same thing. System software and operating system mean the same thing. And then you have this thing called application software. So the term application software or app or program basically means anything you apply. So the word application means to put on something. So the application software is put on the operating system. In other words, I install applications on my operating system. So the operating system is the main program that runs the computer, and we represent it as such. So we're going to draw a circle over the operating system, and we say that it controls and coordinates the computer system. So it controls and coordinates all the activities of the computer system. This is how we view it. But remember, it's still a software, and a software is basically a file that has lines of instructions that are to be executed by the CPU. So these instructions are to be executed by the CPU. So simply put, my computer is basically a CPU, memory, and other devices. That's what a computer is. It's basically a CPU, memory, input and output devices, and storage. These are the four fundamental components of a CPU, of a computer, sorry. So the CPU reads this CPU reads operating system instructions. That's fetch, decode, execute, understands, and then performs the action to control the action of a computer as a whole. So this operating system consists of many pieces of software, which we've been looking at throughout this particular chapter. So here are the slides. So in the slides, I'm just going to skim through real quick. We have this first diagram. And in this diagram, you can see that you have the user, that is you, who is using the computer, and you have the computer hardware. You interface or communicate with your computer via your operating system or the application programs you've installed. You can see here there's a relationship between the user and the operating system, which is basically the interface you're working with. On my computer right now, this is my application menu. This is the interface I'm working with. So I can click things, I can open things, I can drag and drop things. That is the interface that the operating system has provided me with. So an operating system is basically the manifestation of the execution of code that has been fetched and decoded by the CPU. So the operating system provides me with the following fundamental functions. All operating systems provide me with one, a way to control the computer or to pass commands. Pass commands to the system, also known as a user interface. Sorry? We're doing it today. So this is the first function. The second is to manage all the hardware. What hardware? These hardware that we mentioned. So those are the input devices, the output devices, the storage, communication, and memory devices. So the second function is to manage all hardware. So when we say manage all hardware, what do we mean? We mean that every program that is executing will need hardware resources. How we share those hardware resources, who has control over what item at what time, basically creating a timetable for sharing all of these resources is what management of hardware is all about. So remember, the hardware here includes input, output, processing, storage, and communication devices. The third function is to manage all software. So like we said, a computer can run multiple programs at the same time. So for example, on my computer right now, I have a bunch of programs running. So I have my PowerPoint, my web browser, Teams, OneNote, and so on. So who gets access to which resources and whose turn is it to run, and all of these questions are handled by the operating system. So coming back to the slides and proceeding, an operating system is defined as a collection of programs that integrate the hardware resources of a computer and makes those resources available to a user and the user's installed programs in a way that allows the user to access the computer in a productive, timely, and efficient manner. So the designers of the operating system, their goal is to provide you with access to these resources in the most productive manner possible. So that means if we're comparing two operating systems, which one is better than which, what we're actually doing is going to be measuring how productive we are on one device compared to another. As a simple exercise, if let's say, for example, I asked you to write me an essay, and I say, write me the essay on your desktop computer or your laptop versus write it on your phone, which one is going to be more convenient? Which one is going to be faster? Obviously, your desktop or your laptop is going to be better than your mobile device. This is not to say the mobile device is the mobile phone is a terrible device, but it's not, you don't get as much productivity because of the form factor. It doesn't have a keyboard, doesn't have a mouse. The screen is really tiny, so you have to do all of these acrobatics and so on. So the difference between one operating system and another, what makes one better than the other, is in how well it provides you with access to resources so that you're able to perform things in a productive manner. So we've already mentioned the three basic services or functions of an operating system. One, allows users to give commands to the computer. That's what this first point is talking about. Second, manage all software. Third, manage all hardware. So I've just summarized those three. These are the most important functions of an operating system. An operating system also allows multitasking and multiprocessing, which we've already explained. However, there are some additional services that an operating system also provides, including providing an interface. So that's function number one. File management, which we're also going to look at today. Input-output support services. We've already mentioned how the computer does its input and output in a previous lesson. Means of starting the computer. This is basically a function of the operating system. When you hit the power button, it loads up, it boots up basically. Handle interrupt processing. This is how the computer knows that you have given it instructions. So anytime you touch your mouse, you touch your keyboard, there's something called an interrupt signal that tells the computer, hey, this user is trying to interact with you. In the very same way, you can feel somebody touching on your skin, or you can hear somebody calling out your name. It gets your attention. So an interrupt signal is basically a signal that gets the attention of the computer, and you can get the attention of a computer by interacting with any of its input devices. Then there are network services that the operating system provides, how to connect to a network and how to manage that. And then there are services for allocating memory, which we've already covered. We call this process control management for managing the CPU, and we call it memory management for managing the memory. And then there are also security and protection services and administration. So security here means locking files, locking the system, so that you need a username and a password or a fingerprint or a facial scan to actually access the devices. And protection also can mean doing some rudimentary antivirus software, antivirus protection. Then system administration covers who is doing what on this device. So anytime you log on to your computer and you perform an action, the computer actually stores the what, when, and who did it information in what is called a system log. So all of these are services that are provided by the operating system. The operating system is divided into 3 categories. In other words, it's a group of software, as we've mentioned, made up of hundreds of individual pieces of software. However, those hundreds of software can be grouped or classified into 3 groups. One, we call it memory resident. This is the part of the operating system that is always loaded onto memory. Another name for it is the kernel. It is the center of the OS. The second bit is the memory non-resident. That's the opposite of memory resident. So memory non-resident simply means the parts or the programs that make up the operating system that are not always running in the background. So these include utility programs. The word utility basically means something that can allow me to derive more benefit from a particular item. So I gave the example of if a car's primary function is to transport people from point A to point B, then the air conditioning and the infotainment system enhances that experience. So the air conditioner will be considered a utility. The entertainment system, the radio, or if you have a head unit that supports video playback, then all of that will be considered utilities, as they are not concerned with the primary function. They are just support activities or having maps, navigation, and so on. The third category is what we call the bootstrap program. So the bootstrap program is very simple. It's essentially also called the initial program load. So what it does is the part of the operating system that loads the operating system when you turn on the computer. So it's a set of software that, one, checks all your hardware. So the minute you turn on a computer, before the computer actually turns on, there's a system check that happens. So this particular set of software checks for all your input devices, all your output devices, all your processors, your network connection, and everything. And basically, it does a system check of all the hardware. Once the system check is done and complete and everything is fine, then it identifies the partition on your hard drive where your operating system is installed, and it loads the kernel. So this guy loads the kernel. And that's when your computer starts. That's where you hear the welcome chime and your screen lights up, and then you can start using all your input and output devices. Because for every input device you have, there has to be a program that controls it. So before your mouse and your keyboard can work, the program that controls the mouse and keyboard has to be loaded. And that program is inside the kernel. In order for you to be able to see something displayed on your screen or hear something from your speakers, there has to be a program that tells the screen what to draw and the speakers what to play. So it's running in the background and it's part of the kernel. And everything else we've looked at, like process control management and memory management, all of these things are part of the kernel. So the kernel is the fundamental component, but remember, it's not one thing. It's many things. So the whole operating system, hundreds of small software. These hundreds of small software, we've grouped them into 3 categories. The kernel contains the software that operate the primary functions. Those are the most important. Without them, computer is useless. Then you have the utility programs. Those are the programs that help enhance the use of the computer. Make things easier, make things a little bit faster, make things a little safer. And then you have the bootstrap, whose only job, the group of software, their only job is to check the system at startup, make sure everything is fine, then boot up the computer, and then turn off, finish. They only operate at the point in time when you turn on the computer. So the point that I'm trying to reach by revisiting this subject is for you to understand the operating system as a concept. It is a group of files that control or contain instructions that control and coordinate all the actions of a computer. In other words, it's a manual that defines how the hardware of a computer should operate. In the same way, you as a human being, we can say you're made up of the physical body and maybe something like the consciousness or the soul. So the soul is what says what to do. The body is the one that performs the action. So if I wanted to get up and start working, certain muscles in my body have to contract and relax to create that animation of walking. But who decides to walk? It's the consciousness. So a computer is also similar in this regard. The operating system controls all the actions of a computer. It tells the CPU the how to perform this action. So if the computer wants to do process control management, there's a file in the operating system that the CPU has to read in order to know how to do process control management. If I want to display something on the screen, there's a file in the operating system that the CPU has to read to know how to display something on the screen. So what am I saying? The CPU is the main controller of the entire device, and it is able to control all the other components by reading operating system instructions to know how the hell to perform those actions. So don't think of the operating system as a thing that performs an action. It's just a bunch of files or programs with instructions on how to perform the actions. The CPU has to fetch, decode, and execute those instructions in order for them to happen. You get it? So that's the main gist of it. So all the while, we've been looking at what exactly an operating system is able to do. We want to go in deeper to look at specific functions and break down those functions. Now, a computer, basically an operating system, can be built for different purpose categories. So here you have single tasking, single user. Single tasking, single user means a system that is designed for one person and can only do one thing at a time. Most of these systems are now obsolete because computers have gotten a lot more powerful in the past 15, 20 years. So most computers today are so powerful. In fact, most phones are more powerful than many laptops. You don't really need a laptop anymore. If there was a way you could, slot in your phone into a larger display with a keyboard and a mouse, it will work perfectly fine without any issues. But in any case, these different form factors are designed for different environments and different use cases. You also have the single user multitasking. So that's a system that is designed for one person and it does multitasking. So that's most of your mobile devices. Why do we call it single user? Because it's designed for only one user. So if you buy a phone, it only allows you one user account. You don't share a phone, or rather a phone is not designed to be shared. Unlike something like a tablet or a laptop or a desktop, where you can create user profiles. Then you have the mainframe categories, which is computers for, you can say, industry use. So if you have a large, medium, or large company that processes a lot of data, you probably want mainframes. Then you have network servers. These are for organizations that have a network infrastructure. So you want all the computers to be connected and maybe share an internet connection or share resources like printers and so on. You can have those network servers. Then you have distributed systems. These are for organizations that have more than one branch, physical location. So if I have a place like a bank that has many branches across a state or in different countries, and I want to connect them all together, then I will need to use what we call a distributed operating system. So every category you're seeing here has a type of operating system. Let me drive the message home. I'm going to Google here versions of Windows 10, for example. So when I look at the question of the versions of Windows 10, let's see what they have. So, okay, these are the specific builds with the build number. This isn't what we're looking for. We are looking for, let me try this, the same site. So let's see. Usually there's there we go. This is the list we're looking for. So you can see here you have the Windows Home Edition. So this operating system is going to fall under the category of multi-user multitasking, not single user single tasking. It will fall under multi-user multitasking. If it's designed for a home, that computer is the only computer in the home. So it will have multiple people using it, so it will allow you to create multiple profiles. So every feature inside is designed for home use. That means security isn't of paramount importance, although user identity and everything is going to be kept. Then you have the Windows Pro model. This is for professionals. So these are for things like students who are going to be maybe learning some aspects of technology, or people in the working environment, like in an office and so on. So it has certain features that are not available in the home edition. For example, did you know that all the staff members of APU, when you join this company and you start working here, you're typically issued a computer. And when you're issued that computer, the computer is locked by the system administrator. In other words, there's certain things you can't do with the computer. You can't even change your background, your desktop background, if you have a company computer. That's how restrictive it is. So although you guys, most of you will have the Pro version or the home version of Windows, the Pro version has features that you may not be aware of there. That is network lock features. So there are certain things that you cannot do on APU devices. There are certain websites you cannot visit, and there are certain software that you cannot install, and there are certain actions that you cannot perform. So those extra services are only available in the Pro models. In the home, there are things that the Pro can do that the home cannot do, because it's for a different use case. It's for a different environment, right? Then you have the enterprise mode. This enterprise mode is basically for organizational use. So this, in every organization, if you have a mainframe, you will have not a regular operating system, but a server operating system. So this might be an enterprise edition system. So an organization's central server will use a specific version of Windows, not the Pro, not the Home, but the enterprise version. Then you have Windows for Education. So it has tools that are related to educational activities. And then you have the Windows IoT Core. This is for IoT devices and so on. And then you have the mobile and mobile enterprise editions and so on. So for every version, there are certain functions that it can execute that are not regular. So even in this distributed system, there is a version of Windows that is the distributed. So it's all falling under the category of the enterprise editions. So these enterprise editions are going to be closer to the distributed systems. So what I want you to understand is, imagine you have an office that has 3 or 4 different branches, like a bank. So if I go to Bank A and I create an account, the data of all my account transactions and activities should be shared with all the branches. So any branch I go to, that information is still accessible. So that's where you will need a distributed operating system. It will treat all these different locations as one. It will synchronize everything. It's the same thing. You can log into your Google account from any computer, because Google operates a distributed operating system. So I can go to the United States and log into my Google account, no problem. I can go to Africa, I can go to Asia, the Middle East, it doesn't matter, because it's a distributed network. So it doesn't matter what computer I'm logging onto. So this is the nature of a distributed system. A real-time system, I mentioned earlier, is basically a system that allows you to that its correctness of function is time dependent. So it's a system who, when you perform an action, the action is going to be very time specific. For example, if you go to an ATM machine and you try to withdraw money, the minute that money is withdrawn, your account has to be updated. If there's any delay, it can cause problems. So a real-time system will be one that will only permit the transaction to happen in a very short amount of time. If it cannot execute in that short of time, it cancels the transaction. This is why ATM machines, when you've actually set in, I want to withdraw a certain amount of money, you will hear the machine count the money, but it won't give you till it updates the system. Then only that hatch opens up and the money gets to you. If during that process of uploading or updating the data, there's a network connection, the money is not going to come out. That's the nature of a real-time system. It will only complete the transaction once everything has gone through. Then you have, of course, operating system for mobile devices and what we call embedded systems. So this embedded systems, an example of it is this IoT core. So IoT systems are typically embedded. Not every IoT system is embedded, but an embedded system simply means a system whose operating system is on a single chip. So if I have something like a smart TV, the operating system is on a single chip. It's an embedded system. If I have something like an intelligent washing machine, a smart fridge, a smart microwave oven, it will have an operating system which will have an embedded operating system on the chip. So any device that has an operating system stored not on a hard drive, but on a chip, you consider it an embedded system. So the projectors in this class have an operating system. It's on a chip. It's an embedded system. Very simple. So these are the categories of computing devices. So this is where we left off last time. So I'm just going to continue and complete what we have here. When an operating system operates, it performs an activity, and there are what we call degrees of activities. So you can have an interactive activity. What's an example of an interactive activity? Let's say I click on a file and I select delete. My computer might ask me, are you sure you want to delete? Then I'll click yes. Then it will start deleting. I've just interacted with my computer. So that activity is interactive. I do something, it asks me a question, I perform another thing, then it does. So in other words, like I'm pressing back and forward on my keyboard right now, you can see the interaction between me and the computer is changing the slides. As I press back and forth, it's changing the slides. So that's an interactive approach. An operating system can also do what we call batch processing. A batch is a group. So for example, let's say I open up a file, and inside the file, I have 10 individual files. I open up a folder, and inside the folder, I have 10 files. I can select all 10 files and hit delete. In reality, what needs to happen is one by one, the files will be deleted. But when I'm given the instructions, I don't say right-click, delete, right-click, delete, right? No, I select everything, and I then hit delete. So for example, if I have this folder here, where I have all the slides, I can select this file, right-click, and I can say delete. Then go to the second one, right-click, delete. I can do this one by one. Or I can select everything as a batch, and I can just say delete. So if I do this now, I've selected everything, I'm deleting, I have a batch operation. So in the background, the operating system is still going to delete them one by one. But I've selected them as a batch, and I've sent it out. Does that make sense? Now, I'll give you an example of batch processing. Everybody is aware, maybe not everybody, if you have ever worked, you understand that you earn a salary, and your salary is paid once a month. In Malaysia, I think the date for payment is the 28th of every month. That's the date of payment. Now, I want you to imagine, Malaysia has about 33 million people. We can say that about half of those people are adults that are working in a salaried job. And everybody, half of that 33, about 15 million people, let's say 10 million people, have to be paid on the 20th. So that's 10 million operations by the different banks. How does the bank do that? That's a lot of processing of information. So what happens is, on the night of the 27th, they create a batch process. So a list of all the people's names and how much their companies have paid them. So overnight, it begins to perform the operation. This is why every night, usually at midnight, if you try to open up your bank account, you won't see your history, because they're backing up their systems, they're updating certain things. So between the hours of 12 and 2, usually you won't get any operations from a bank, because that's when they do their batch processing. So part of their batch processing has to do with, if it's on the 27th, they're doing money transfers for this 10 million people. If it's on a regular day, they're performing backups. If there are updates to perform, they're performing updates and so on. And all of these are batch processing, batch operations. So a batch just means a group. Then you have what we call the event-driven operations. So an event-driven operation is, take, for example, here I'm on PowerPoint. If I right-click, a menu pops up. So the right click is the event. An event is anything that happens in a computing environment. So an event-driven action is an action that is triggered by an event. And an event is any action that I perform. Left click, right click, press something on my keyboard, and so on. So these are the types of activities that an operating system can engage in: interactive, batch, and event-driven. Operating systems are also, in some cases, tied to a specific hardware. On my computer right now, I'm running macOS. You cannot install macOS on a mobile phone because macOS is hardware dependent. And the only hardware the macOS is designed to work on is on Apple hardware, specifically the ARM architecture, because the CPU is of the ARM variety. So an operating system may be dependent on a piece of hardware or a hardware architecture. You cannot install an Android operating system on a desktop computer. You can emulate it, but you can't install it on that actual hardware. It wasn't designed for that. So some operating systems behave like that. And yet there are some operating systems that they don't care about the hardware. So for example, Linux, the Linux operating system, it's pretty much hardware agnostic. You can get different versions of Linux to learn on basically anything. There's this thing called a I think it's a T82 calculator that you can basically install Linux on it, basically. You can run Linux on literally nearly every kind of hardware. So some operating systems don't particularly care about the hardware. Now, the other services and facilities that are provided by the operating system include file management, which we're going to be looking at in a couple of minutes, process control management, which we've already looked at, memory management, which we've also already looked at, which includes scheduling. And today we're going to also look at secondary storage management. So the reason why I revisited this section is to show you that everything we've been studying in the past 4 weeks is all under the operating system umbrella. So today we will do file management and storage management, but we've completed all the others. We've looked at CPU scheduling and so on. For network and communication and system protection, these are going to be covered in your introduction to networking module. I think you're doing it next semester, right? You're not doing any course called Introduction to Networking right now, are you? You are? So that's that bit. Anything that has to do with networking is under that bit. So we've completed the rest, except for these highlighted in two. So that's what we're going to be looking at. So let's quickly conclude here. There are many different types of user interfaces. I'm sure you're aware of the command line interface and the graphical user interface. So here's an example of the command line. So here I have my terminal. If I go full screen, you can see here, my computer now allows me to interact with it. And this is a legit operating system, this black screen with just text. So if I wanted to see the calendar, I can type in the command for the calendar and I can see exactly the details of the calendar here, as you can see. So the idea here is I have multiple interface types and ways I can interact with my device. If I wanted to see the list of files in a particular folder, I can type out the command and I'll go ahead and see the list of all the folders and directories and if there are files in that particular location. And I can change the directory and go to, let's say I want to go to my, do I see downloads? Let's say I want to go to my downloads file. I can do that and I can then launch a command to show me all the items in my downloads folder, like so. So it's a way of interacting. This is a command line interface. For a graphical user interface, the same thing. I can open up this window using my file manager, go to downloads, and you can see the list of files that I have in my downloaded folder, like so. So let's proceed. So that's that about the types of interfaces. Another set of interfaces that you're also familiar with is voice command. So for the voice command, the Apple guys have the Siri, the Microsoft has Cortana, the Google guys have Gemini. And I think now Microsoft has partnership with ChatGPT. No, actually, it's Apple that has a relationship with ChatGPT. Yeah. Copilot. No, Copilot is the software. The actual AI is called Cortana. So I actually have Copilot also installed here. That's this guy here. So the software is called Copilot. The engine, I believe they call it Cortana. If they've not changed it, perhaps they've changed it. So these are basically AI tools that also allow voice commands. That's basically what I'm saying. So I can interact with my computer using voice commands. So just like I open up this downloads folder and I check for a file, I can use voice command to talk to my computer and I can say open file so-and-so from so-and-so location, or transmit a message for so-and-so, or put a reminder on this calendar date and so on and so forth. So that's another aspect. So when it comes to interfaces, there are many types of interfaces. Let's make a short list of the different user interfaces that we have available. So one, we said there's the very popular command line interface, CLI, command line. Then there's the graphical user interface, GUI. Then we mentioned there's the voice, which includes Siri, Google Now, Cortana, and so on. Then we also have something called a gesture-based interface. So the gesture-based interfaces are basically interfaces that you control by movement. A very good example of that is the Nintendo Wii, if you remember it. It was a very popular console back in the day. I think it's maybe 10, 15 years ago. It was very, very popular and very, very successful. So I just want to show you an image of that. So this is the Nintendo Wii, and you can see the controller is basically, it's called the Wii Remote, and it has a gyroscope inside that you can control actions on the screen by movement of that particular controller, not simply by pressing buttons, but by movement of the device. So if I went here and let's say Nintendo Wii demo, you begin to get an idea of what I mean. So I'll shut down the audio and you can just see this guy on screen. As the guy is playing, he's moving the actual joystick and it's controlling the objects on screen. So this is what we would call a gesture-based control, right? So you can see here he's flying an aeroplane and the movement of the actual controller controls the actual aeroplane. So Nintendo is a company that is known for these types of innovations. So they're a very forward-thinking company. So that's the gesture-based. You also have what we call the virtual reality, VR, and you also have the AR, augmented reality. There's also what we call mixed reality. And there is also the menu-driven. So with VR, you've heard the term virtual reality. So if I were to come here and say, let's say we say PS2 VR demo, for example, and we see, I think this is an ad. So what does the VR system actually do? In a VR system, you, the user, are taken and placed inside the virtual environment. So you go into a virtual environment. And to go into this virtual environment, you make use of certain hardware tools. So there's a display, which is a 4K HDR display. And then you have a bunch of joysticks that are connected to your hands that control the, so it incorporates some aspect of the gesture-based control that we mentioned. And there are also environmental sensors to sense your movement and your head position and so on. So you can see, they're not really demonstrating it, but you can see how this actually works. So here, holding the Joy-Con, the joystick transforms into a gun in the virtual environment. So it puts you into the virtual environment. So this is virtual reality. Augmented reality, on the other hand, instead of you going into the digital environment is brought out into your real world, and you typically see it through a screen and a camera. So here you can see in this demo, this guy is using his phone, and his phone has noticed the image on his that it's viewing through its camera, and it's going to now bring in digital assets into that. So this is opening a cupboard and it's showing him something. This is augmented reality. In real life, it's not actually happening. It is the computer taking information about the real world and superimposing some other artifact on it. Let's take a look at another example of this. If, let's say, you're walking down the street and it can put in these digital assets into the real world. So this real world is going to be, the digital world is going to be taken and put into the real world for you to view through a screen and a camera, as it were. So it adds information to the real world. So it's the opposite of virtual reality. Virtual reality, you go into the virtual world. Augmented reality, the virtual world is brought out into the real world. Mixed reality is a certain feature of augmented reality. In the augmented reality, you can see the information in the in your real world space, but you can't interact with it. Mixed reality allows you to interact with it. That means if you have a system where these artifacts are on display, you can actually touch them and you can move them around. So let me show you an example of Microsoft HoloLens, which is basically mixed reality. So this has been in production for quite a long time. I should suspect by now they should have released it, but it's still not out in the market. Not sure why. So here you have this Microsoft employee. He's wearing the HoloLens, and the HoloLens is essentially close to your Apple Vision, except that it's much older. So this is, I think this demo, you can see this guy is more than 8 years ago. So Microsoft already had something. It's still not in the market. I'm not sure why. So in mixed reality, it's augmented reality plus you can interact with those objects. So here you can see this guy is actually playing a game and he's shooting down a digital wall, and you can see the digital wall, the digital assets coming out, and he can interact and manipulate this digital asset. So you can see he's actually shooting things in his living room, even though he's the only one who can see it. So it's augmented reality mixed with the ability to be able to manipulate those digital assets. So that's what we call mixed reality. So mixed reality is augmented reality plus the ability to manipulate these objects. So you might be thinking to yourself, okay, it's HoloLens just a game? No, it's not a game. It's an interface. So here in this demo, you can see this lady. She's demonstrating how you can interact with menu objects. You can press buttons, you can click, you can drag, you can drop. And here you can see she's actually running Teams in this mixed reality mode, right? Let me just rewind a little bit so that you can get the idea. So you can see Microsoft Teams and a music software that she can interact with, and she can pick it up. She can place it in different places. So here she's controlling Microsoft Teams. She's scrolling through all through the mixed reality headsets. So those are examples of user interface types. Then you have the menu. The menu driven is basically what you have on your ATM. You go, the screen changes like a book. So when you put in your PIN, the whole screen changes. You select what type of transaction. Is it cash machine or ATM? You press, the whole thing changes. Do you want to withdraw or deposit? You press, the whole thing changes. So that's typically a menu-driven interface. And that, for the most part, is that. The last bit we're going to be looking at, so here you have all the different titles that we've already looked at, the process control management, memory management, and so on. We've already mentioned this. The last thing we'll be talking about with relation to this particular topic is the configuration of these operating systems. So we've said an operating system has an architecture. Different types of operating systems have different architectures. So you have three main ways of configuring an operating system. You have the monolithic, the hierarchical, and the microkernel. And you can see examples of each operating system that uses this particular configuration. Monolith is a word that means single, gigantic. Mono means single, lithic means gigantic. So one big core. So the monolithic configuration basically can be found in the Linux operating system. And what it is, it's that the three parts that make up a computer a computer's operating system, the memory resident, memory non-resident, and bootstrap. The memory resident is the core of the operating system. So in a monolithic configuration, the kernel is very large. In other words, it's a big program. So in that configuration of operating system, you have a very, very large and detailed kernel that is capable of many, many, many functions. So here's what it would look like. You can see in the center here is the kernel, and outside the kernel, there's a shell. What is the shell? The shell is the interface by which you can communicate with the kernel. And these little blocks here are the utility programs that we mentioned. Remember, every operating system has these 3 bits. The memory resident or the kernel, the memory non-resident, and the bootstrap program. So here you can see the kernel, and then you can see the utilities. The bootstrap, we only see it when you are turning on the computer in the beginning, so it's not represented here. So the idea of a monolithic kernel is that the kernel is one, instead of having multiple programs like we mentioned, it will be one super program with multiple sections of code that handle different aspects. There's an advantage and there's a disadvantage to that. Imagine having one list that contains everything versus multiple lists that contains everything. So you will begin to appreciate it when we look at the next example. So here's a hierarchical model, and the Windows typically uses a hierarchical model. So how does that work? The operating system's kernel is divided into segments that are interdependent on each other. So here you can see the user interface is related to the commands and utility, which is related to the file services, which has a relationship with network, process management, resource allocation, and virtual memory, and the I/O system. Everything is kind of tied together. The good thing about this architecture is that anytime you install a new program, the new program operates as if it's a native program. The operating system is already installed on your machine. It's running very well. Any program you install will operate as if it's the operating system running at the same time. It won't be seen as something external. So whatever you install becomes part of the operating system. That's the good thing. The disadvantage is if any one of these components fails, all the other components that are relying on it also fail. So for example, if the resource allocation fails, it will affect the input-output system and the file services and every other thing that is related to it. This is why on the Windows system, you get the blue screen of death. When a Windows computer wants to freeze or hang, the entire thing freezes and hangs, and you have to basically restart it. For those of you who have a Mac, you will know that in fact, I think in my 15 or so years of using a Mac operating system, I've had the Mac crash on me just twice, like complete crash, only twice. And it was because of a hardware failure. In other words, when Macs crash, the operating system doesn't crash. Only a component crashes, and you can restart that component. You can't do that with the Windows systems because everything is interdependent. Now take a look at a Mac operating system's architecture. This is what it looks like. So you have a microkernel. Micro is opposite to monolithic. Monolithic means single and large. Micro means tiny. So in other words, the most important functions have been reduced to a very small program. And then every other extension is added onto that. So all the other functions are added on as components. So here in this case, if the file manager crashes, it doesn't take away the microkernel or the other components. Only that one thing crashes, and you can restart it and continue business as usual. Your computer will still be running. It won't shut down. One aspect of it will shut down, but you can restart that aspect without turning off the computer. Whereas with the Windows, when one thing goes, the whole system goes, and you have to restart everything from scratch. So I hope that's clear. So that's just the details of the architecture of these systems. We've already looked at the types of operating systems, and that's that. So we will return now to the last 2 bits, which is the file management and secondary storage. But before we do that, let me just quickly ask, is there any questions from the people at home? Can I get a thumbs up if everything is clear from the people at home? All right. So we will take a look at the next two subtopics, which is file management and disk management. So what is file management? It's important to note that when we talk about memory management, the concept of memory management essentially has to do with how we share space on a computer. So let me just go back to my OneNote here. In the previous lesson, we discussed memory management by first understanding that memory is just this large space, and we can partition that space using two techniques, which is fixed and variable partitioning. So with fixed and variable partitioning, we explain some of the concepts and some of the differences. I'm going to add something to that conversation. When we're dealing with fixed partitioning, here's one condition that can occur. There's something we call fragmentation. So let me go ahead and draw it out here. First, I will start by drawing a block to represent memory. And we're going to say this is a fixed partition. And the fixed partition that we're using is let me correct this. I'm trying to draw to scale. So this is 100 kilobytes. This is 200, for example. And then this is 300 as our example. So I want you to imagine if I have a program P1 that is loaded into this 100 kilobyte block. And let's say P1 is actually 80 kilobytes big. What that means is internally, we will occupy just a subsection of this space. In other words, there will be some free space inside here. So the free space is internal. The partition is like a compartment. Think of it like a drawer, a cupboard that has a fixed size. So if I put an item that is smaller than the drawer, I'll have these small spaces on the sides. And that's what's happening down here. So all of this space here is free space. But in operating system memory management, one program is allowed access to only one location in memory. In other words, one process, one location. That means I cannot put two processes in one memory location. Why? Because this location only has a single address. So if I put two items in one location, how do I fetch an item from that location? I can't. Because if there are two items given in the same address, how do I know which of the two items I'm supposed to pick up? So as a policy, you have one process, one partition. Because of that rule, it means this free space down here is essentially wasted space. It cannot be used for anything. So we call this a fragment of space. And because it's inside the partition, we refer to it as internal fragmentation. Internal fragmentation. This is for fixed partitions. What about for variable partition systems? So for the variable partitioning system, if I have a similar example where I have a block, remember the way this guy works is once a process comes in, we allocate the space to it. So here we have the P1 process, which is 80 kilobytes. It has been allocated here. So we allocate exactly the space it needs, whereas the rest of this is free space. If another process P2 comes in, then we can allocate exactly what it needs. So let's say P2 needs 250, then we allocate a size of 250 kilobytes. And we continue to do this as time goes on. So as programs are coming, other programs are finishing. So let's say in this example, P1 is done. If P1 is done, then this 80 kilobytes is free space. So now I have free space here and free space here. So as processes are coming, maybe another process P3 comes in. And let's say P3 let's say P3 needs 60 kilobytes. Remember, this partition here is 80 kilobytes big from the previous P1. So it means it will occupy this space. So here I will have 60 kilobytes occupied, which means here, down here, I have a 20 gigabyte fragment. But the fragment is outside the partition. So technically, it's usable space. Unlike with internal fragmentation, where the partition it's already in use, nobody else can use this free space. Think of it like a parking lot, and a person pays for a slot and goes and parks a bike in a car spot. He's paid for it. If he puts his bike, you cannot come and bring another car and put it in. It's not going to be enough space. And if you park a bike, there's wasted space. Do you see what I'm saying? If I'm booking for a parking space, it's one space per person per payment. So if I put a car there, fine. But if I put a motorcycle, it's still fine, but there's a lot of wasted space. But that wasted space is inside what I paid for and nobody else can use it. That's the case of fixed partitioning with internal fragmentation. With the case of variable partitioning, the space is outside of the partition, but it's too small to be usable. In which case, we refer to this as external fragmentation. So I hope this concept is clear. Internal versus external fragmentation. We find internal fragmentation in the case of fixed partitioning systems and external fragmentation in the case of variable partitioning systems. But remember, when we talked about this, for fixed partitioning, we introduced the concept of paging. Paging doesn't suffer from fragmentation because everything is broken down into fixed sizes. The programs are also, the programs and processes are also broken into fixed sizes called pages, and the memory is broken down into a similar size called frames. So a page is equal to a frame, so everything fits neatly and nicely. So we don't typically have the problem of fragmentation on these types of systems. So that's the introductory caveat. So when looking at the storage space, the memory, the operating system needs to figure out how to partition. And after it has partitioned, it needs to understand or come up with a method of how to store files and data onto the system. This is what file management is all about. So when we talk about a file managing system, we are talking about how to prepare this memory device or a storage device. So when we talk about memory, remember memory is a type of storage. In the case of file management, we are specifically talking about the hard drive, the storage, not the memory. But the memory also has to implement the architecture of file management that we decide to use. It'll make sense in a second. So what is file management? Well, what is a file? A file in a computer is essentially a document that consists of a sequence of zeros and ones. This is what a file is. So a file can be a data file, and it can be an application file. What's the difference? A data file contains zeros and ones that refer to data, and an application file contains zeros and ones that refer to instructions. That's all. So if we take a look here at the concept of file management, here's what we're going to be discussing. What are the objectives of file management? The properties, the functions, and the different types. That's what we're going to be looking at. So at the end, we should be able to explain the usage of file management in operating systems, distinguish between the different types, and identify the advantages of the different techniques. So let's go through it nice and slow. You can relax. This is not a complicated subject. However, you need to have a prerequisite understanding. The concept of managing files is very similar to what you will find happening in a library. What does a library contain? I'm asking a question now. What does a library contain? What is inside the books? Huh? What is inside the pages? At the end of its information, and information is made up of data. So at the end of the day, what does a library contain? Data. But the way the data is organized and arranged will determine how easily you can access it. For example, the data elements are arranged using the rules of language. So each data element, you create sentences. So a data element can be a word. You group a certain number of words together in a particular format, you get a sentence. A group of sentences forms what? Group of sentences. Paragraph. A group of paragraphs, a section. A group of sections, huh? Chapter. A group of sections will form a chapter. A group of chapters, a group of chapters, a book. A group of books, that means if the book has part 1, part 2, part 3, a group of books, a collection of books, library. You get the idea? Now, inside this library, the data has been organized such that data elements are in sentences, sentences are in paragraphs, paragraphs are in sections, sections are in chapters, chapters are in books, books are part of collections. The overall collection is a library. Then each book inside that library is identified as a single entity. For example, I won't go to a library looking for a section. Typically, the section is in a book. The itemized values or components inside the library is a book. So whatever I'm looking for, I have to pick up a book. So how does the library arrange these books? They arrange them on shelves. And the shelves of a library are partitioned into sections. So you have the science, the business, the technology, and so on and so forth, different sections. And inside those sections, the books can be arranged based on book title or author name. So I can have alphabetical arrangement of books by author, or I can have alphabetical arrangement of books by their own title. Or I can even have them arranged by published date or publisher. You see what I'm saying? So how I arrange information inside the library is the library management system. And what is the job of a library? To allow people to retrieve or find data. So if I go to the library, the best library is the library that allows me to find the information I'm looking for as quickly as possible, as easily as possible, and it's also the library that can store as much information as possible. This is exactly the same conundrum with a file management system for a computer. So at the end of the day, if we say data is in a library, what is inside the storage device of a computer? Data, zeros and ones. The zeros and ones form, in computers, 8 bits make up a byte. 8 bytes make up a, 4 bytes, is it 4 bytes? Yeah, 4 bytes make up a word, and so on. So you break up the data, and the data combines to form different files at the end of the day. A group of files can then be stored inside a folder. A group of folders can be stored inside another folder, and so on and so forth. So the file management technique in an operating system basically refers to a set of processes and techniques that are responsible for creating new files, organizing how we arrange them, accessing how we get access to them, manipulating how we move them around, and controlling files stored in a storage device. That's what file management covers. The technical ability to perform these actions. So how does it work? So you can see here, an operating system will have a storage device. That storage device, typically a hard disk drive, or in modern terms, a solid state drive, will have a filing system. The file system is the description of how to store files inside this storage device. In the same way, the library can section off the books into separate categories, and in each category, it can arrange things according to author name or title of the book and so on. So also the hard drive has to be sectioned so that it can store these data files. And these data files can be regular files or collection of files, which is called a folder, and so on. So you can see some of the attributes here: the size of the file, the type of the file, the location, the hierarchy, and the address of the file. All are contained in the filing system. And the files can be stored inside this filing system as a folder, for example. So the objectives of file management, in other words, the reason why we do file management are as follows: file encryption. Encryption is a technique of hiding data. In this case, we use encryption to keep our files private. The encryption, to encrypt means to change the nature of data so that it is unreadable except by people who have something called the encryption key. If I have an encryption key, then I can unlock the data and I can read it. So think of encryption like locking a door. If I have information inside a room and I lock it, only the people with the key can access that information. That is encryption. So what we're saying here is, in an operating system, one of the things that operating systems tries to do is to protect your files that you've saved on your storage. So file management includes a feature to protect those files you've put in by encrypting them. What this means is, if my computer has a username and password, it means you can't turn it on and access any of my files unless you have my username and password. But what happens if somebody breaks open my computer and physically removes my hard drive and plugs it into another computer? Then they don't need the username and password of my operating system. They have access directly to my hard drive, right? So normally they'll be able to read it. But now, because of file encryption, they won't be able to read it. Only my specific operating system. And when I say my specific operating system, I don't mean if I have a Mac OS and the guy steals my hard drive and puts it in another Mac OS, they can see it. No, it has to be my account using my encryption key. So it means even if somebody steals my hard drive now, it's useless. You understand what I mean? So file management implement security by permitting
maybe a card defunction.
Next point.
And something happened.
File retrieval. If I want to retrieve a file, how do I do it? One, I have to have a way of visualizing the file, and I have to have a way of probably searching for the file. So let's say right now, I open up this is my, where is it? Here. This is my file explorer. Let's say inside my downloads folder, I have a specific file that I'm looking for. Let's say I'm looking for a file called The Legend of Zelda. Now I can go through this file using my file management utility. The Mac operating system file management utility is called Finder. And it allows me to visualize folders and files. You can see here the blue is a folder, whereas the whites or other colors are regular files. And I can open these folders and I can access and view these files. So if I'm looking for something, the first step is I need a file manager to allow me to be able to view what I'm looking for. Secondly, I can organize this by clicking on the Names tab here to arrange everything alphabetically, from folder to files. Or I can organize them by size, which is the biggest. So I know my Legend of Zelda file is really big, and here it is, 7 gig. So I've arranged it based on size. So all of these sorting allows me to be able to identify things that I may be looking for. I can also arrange based on type. So all the Word documents will be together, all the PDFs will be together, all the MP4s will be together, and so on. You get the idea? So this is all part of the concept of file management in terms of file retrieval. So here, if I wanted to search for my Zelda file and I typed in Zelda, it'll filter out everything, and just show me that file called Zelda. So this is file retrieval. So I can double click on that file and retrieve it or open it. Data sharing. What does that mean? It means I can share that file. So I can literally go to this Legend of Zelda file, right click it and hit on share. And when I hit share, a menu will pop up and say, what do you want to use? AirDrop is my Apple's Bluetooth. So if I have another Apple device that has Bluetooth, I can turn on the AirDrop, or I can send it through Apple Messages or through my notes, or I can edit and then add other attachments. I can send it via email and so on and so forth, or even via WhatsApp, although WhatsApp won't allow you to send a file that I think is larger than 60 meg. But I can add an extension to this menu of my file manager to allow me to share using also other programs that the operating system is not familiar with. In other words, I can increase this list. Then file compression. I'm sure everybody has heard of a zip file. A zip file is a technology that allows you to reduce the size of a file. How does it reduce the size of a file? The files are made up of zeros and ones. You can apply a mathematical algorithm to these zeros and ones to identify a pattern, and you can shorten it. By shortening it, you reduce the file size, and by reducing the file size, what happens? You can store more things in less space. So if I have a zip file, or if I zip my files, I'll end up producing more space on my storage device, which allows me to store even more files. The only disadvantage is anytime I want to look at the file, I have to unzip it. But the memory devices are so fast now, it doesn't matter. I can unzip a 7 gig file in less than 4 seconds. Just double click it, brrr, it's done, literally. Modern devices. So that's file compression. Space management. It can allow me to organize my files. Keep in mind, as I'm seeing these pieces of information, these files are all in different locations in my hard drive. Just because they appear next to each other does not mean they're next to each other in the hard drive. This is just a visual representation. In the same way, if I were to print out the attendance list of this classroom, the names are alphabetically. It doesn't mean the guy the two names that are next to each other are sitting together in physical space. So also what you're seeing here is not real. It's a representation of what is inside my hard drive. And that's what the file manager does. It tries to show me in an efficient manner the data that I have stored inside my hard drive or my storage. So that's the space management bit. File auditing. Who created this file? When was this file created? When was it last accessed? When was it last modified? All of that, the file manager stores that information. File versioning. I can have a file. When I created it, let's say I created it today, I save it. Tomorrow, I open it up, work on it, save it. Next tomorrow, and so on, like I'm working on an assignment. So every few days, I open up the same file, I edit, I add some information, I change. That file will have several versions. That depending on which operating system you're using, you can actually switch back to the last save state. So Macs do it. So I can work on a file for a month and I can go back in time every single time I worked on this file and see a different version of the same file. I can actually do that. So the file manager allows you to do that. Data security, it protects the file. You can encrypt like we've mentioned. File organization, that's where I sorted things out based on name, based on type, based on size. And I can also have backing up software. So the Mac OS comes with online storage. That's Apple iCloud that I can use for online backup. So the file manager works with that cloud storage to actually do that. So that's the objective of file management. Now, the methods or the techniques that a file manager can implement can be, the device itself can be sequential, which means your storage device only stores things in sequence. It can be indexed or it can be direct. What's the difference between the three? When we talk of sequential, I want you to imagine a Chinese scroll. Let me show you an image of a Chinese scroll. A Chinese scroll is basically a piece of paper that it's rolled up. So you can see images of it here. It's rolled up. And when you want to actually read it, you unroll it. Now, the trouble with it is, although you can have very long sheets of paper with a lot of information, you can only access that information sequentially. In other words, when you begin to unroll it, you can start seeing the top. If you want to read the bottom, you have to unroll the whole thing, and it takes time to unroll the whole thing to get to the bottom. So this is why we call it a sequential device. So computers used to have what we call magnetic tapes. So magnetic tapes are basically also rolls, like the Chinese scroll. It's lined with magnetic material, and computers used to use this before. So let me show you the Commodore 64, which is the first computer I ever encountered. This was a computer in the 80s. This is the tape drive. So the first game I ever played on this Commodore 64 was Ninja Gaiden, believe it or not. Ninja Gaiden on the Commodore 64. So how we used to play it is this is the computer, it's just a keyboard, no mouse that time. Because all of the computers were command line interface only, black and white screen and text. No keyboard and no mouse, only keyboard. So you would connect this thing to your TV, and then you'll get your Ninja Gaiden cassette tape, and you plug it in and press play. So just like your PlayStation shows downloading when you put a CD, that's literally what happens here. The tape will start to play, and the data from the tape will be copied into the memory of the device. And then once that stage is done, the tape will automatically stop, and then you play stage one. When you finish, it will tell you press play again. So it starts loading the second stage, and it does that continuously. It's a sequential access device, the tapes. That's sequential here. Everything is stored step by step. So if you want to read, you have to go through the entire thing. Indexed. An index, it's like when you know when you have a textbook, what's the first section of a textbook? The table of contents. The table of contents shows you the names of the chapters and where they are located inside the book, their address. So you can have a file management system on a computer that implements indexing on the storage. So that means on my hard drive right now, if it's indexed, it means the first section of my hard drive is a table of contents. So when I come here, you know what I just did just now? When I search for this file, Zelda, how many seconds did it take? I'm going to do that again. When I come to search and I type Zelda, how many seconds does it take? And I can search my entire Mac. When I search my entire Mac, this is files that either have the name Zelda or files that have the word Zelda inside them. Everything is given to me in just a few seconds. How the hell is that possible? My hard drive is 512 gig. How do you search that fast? It's not possible. Because every time you create a new file, the file is indexed. To index a file means to take its name and to take a summary of its contents and then to store it in the table of contents. So when you search the index, not the file. So from the index, it will tell you where the file is actually located, so it picks it up. I hope that makes sense. So that is the concept of indexing. Then direct access devices are your solid state drives. So now these are devices that are like books. You know, if I open up the table of contents of a book and I see chapter 2 is on page 72, I can just skip to page 72 by just flipping. That's how a direct access device works. The opposite of a direct access device is a sequential access device. So the Chinese scroll compared to a regular textbook. With the regular textbook, I can flip and open to any page really fast. But with the Chinese scroll, I have to unwrap it. It takes longer to unravel the paper than it is to flip through pages. So that's the difference between sequential and direct access. Direct access means I can jump from page 1 to any other page in the same amount of time. I can flip the pages. So these are the techniques that a file managing system can implement. Now, the names of the actual file management techniques include FAT or FAT, which is File Allocation Table. This is one of the oldest. You have NTFS. Both the FAT and the NTFS were designed by Microsoft. So for the let me show you, for the Macs and the Linux systems, Macs and Linux are very similar. if you wanted to, say, create a partition, you can create a partition. You can see the Mac uses an APFS system. This is an APFS system. That's the name of their own partition. But it also supports other partitioning techniques. So there's FAT, there's FAT32, there's NTFS, and there are quite a few. We can Google them. There are quite a few. But the point is, each one has a specific way of operating. And you have, of course, the distributed, which is the online version. So once I share this document with you, you can come and read the fine print. But that's basically it. So the advantages of file management includes, one, improved organization. I can arrange things as I'd like, put things into folders and so on. Let me show you what I've done. In one of my folders to do my work, if you come here under lecture, you will see not only are the files, are the folders given appropriate names, I also have a color tag associated with each folder for quick reference. So if I go into, for example, management, I have everything arranged, and inside there I have things arranged, and so on. So it's all nice. This helps me with organizing my work. So I can have things arranged appropriately, just like a library would. Data security. I can protect these files by encrypting them in real time. Let me show you an example. Here, I'm going to arrange this by date. I recently downloaded I think I deleted it. I recently downloaded my bank. Yes, all right. So here it is, my bank statement. So this bank statement is a file. So see here, I can open up any file I want by previewing it. So this is a video file that I'm actually previewing, right? So I can open this file and preview it, no problem. But if I try to open and preview this PDF, it says, hey, we need the password. That's data. That's data, basically the security part. It's not encryption. The file has been encrypted, but this is data security. Every file here is actually encrypted. It means if you remove my hard drive and you put it in another computer and you try to open this file, it won't open. It's only opening because it's on my device. But this particular file has an extra layer of security where you actually need a password to open the file, even for me. So that's the difference between just encryption and data security. That's this. Data sharing. I showed you how you can share the files. Backup and recovery. Some file utilities allow you to do that. On Windows, you have something called this, what's it called? Huh? Not OneDrive. That's the online storage. I'm talking about the one that makes an image of your entire computer and you can restore. I think they call it System Restore. Windows System Restore. So if you have a Windows system, every time you install a new piece of software or you change a piece of hardware, the operating system will take a snapshot of all its configuration for that day. So if your computer crashes, you can restore to an earlier point. In case you didn't know, your Windows systems actually does that for you automatically. So there's backup and recovery, and then compression is the zip files we talked about, and versioning is that you can have these different versions. So these are examples of file management software. On Windows, it's called the Explorer. So if you're using a Windows computer, your file manager is the Explorer. If you're on a Mac, which I am, it's called the Finder. And if you're on Linux, it's called the File Manager, basically. There's also what we call network attached storage. This is a storage device that is physically connected to a network that you can access. Now, many people, you students, will typically have a pen drive or an external hard drive to store your movies and your entertainment, because your computers typically won't have enough storage on board. Now, imagine a situation where you've graduated, you have a house, and you want to download movies. So take, for example, I'm downloading this movie, this Dune movie, and I'm downloading the high quality, and you can see this guy is 31 gig. So this movie that is 31 gig, it's 31 gig because it's in HDR format, which is a very high quality recording. So imagine my computer only has 512 gigabytes of storage and one movie is 30 gig. If I have 10 movies, that's already 300 gig just for 10 movies. That's all of my storage gone. So if I wanted to have a catalog of these movies, I might opt for an external hard drive. The problem with the external hard drive is I have to plug it into my computer in order to be able to access that file. So let's say I'm living in a family house. So I have maybe my wife, my kids, or whatever. And I want everybody to be able to have access to that library. What can I do? I could install a network attached storage. So what is a network attached storage? It's a device. So I'll just Google it so that you can see it. So this, oh my God. I never thought that. Thought this guy was dead already. Anyways, in case you people don't know who this is a very popular rapper of the early 80s. Network attached. There we go. So this is what the device looks like. It's just a bunch of hard drives slotted in, and you connect it to your network. So it allows you to access from any file manager software. So if you have a smart TV, your smart TV can have a file manager software installed that you can straight away stream the movie directly from your network attached storage. And everybody in your house that is connected to your network can also stream. So you can have your music library. I don't know if you guys still download MP3s. Now you have Spotify and Tidal and all these other music services. Once upon a time, we used to have to download the MP3 files, and you create your own collection. So back in the day, there's still people that do that. So you can have everything, and you can stream it directly to your TV, to your audio systems, or to your laptops, or to your mobile phones, if you have the appropriate software. So that's what network attached storage is. It's just a hard drive installed in a component that is connected to your network that you can access anytime you want. Then, of course, you have the cloud-based, which is the OneDrive for Microsoft, Google Drive for Google, and Apple Cloud for the Apple, and there are others. There used to be Dropbox and a few that were popular back in the day, but most of them are dead now. Then you also have what we call content management systems. An example of a content management system is our Moodle. We can upload files and share them using the network environment. You also have what we call source code management systems. Now, a source code is basically your program instructions. There's a website called GitHub. So GitHub is a repository that allows people to share code. So I'll show you an example of a GitHub project. So this GitHub project called Whiskey is a piece of software that I downloaded recently. And what it does is it allows you to emulate a system. So I was emulating Steam. For those of you who know Steam, if you don't know what Steam is a service online that allows you to create an account and download games. So it's for PC gaming. So it's a service. It's like a shop, essentially. It's a software that you download, and it's a service that you register for. So when you purchase games, it allows you to manage your games. It's like file management for games online. So all of this, because Steam is, there are some games that are Windows only. If you want to play your Windows games on your Mac, you have to emulate. To emulate, I had to emulate Steam. So I emulated Steam using this particular software called Whiskey. So Whiskey is a source code that was developed by a user online or a group of users online, and they share the file with anybody who wants to work on it. So you can download the file, edit it, and recompile it, or you can just download the build, and then you can go ahead and install it. So when you install it, you can use. So this is a code repository. You can do all sorts of interesting things here. You can change the operating system of your phone. You can install a newer version of Android by wiping off your device. They call it flashing. You can do all sorts of interesting things with these tools. So these are the code management systems. And then you have, of course, your typical database management systems, which all of you should be familiar with. Are you doing any database courses right now? Yeah, so you already know what that is. So that's basically what a file manager is. It allocates files by reading them from hard disk, and depending on whether you're reading or writing, and the file manager deallocates a file by using the file table. So what this is actually saying is very interesting and important. Do you know what happens when you delete a file? When you delete a file, it doesn't actually delete. Deleting a file is like going to the index page and just canceling out its name. The actual file is still there. So let's say right now, I go into my files and I select one of this and I hit delete. So let's say this operating system I've deleted, right? You just saw that. Let me bring it back. I just delete it now. Once it's deleted, it's still on my hard drive. I've just removed it from the table of contents. So deleting isn't really deleting, in case you didn't know. It's just removing it from the index page. It means you can't find it, but the actual file is there. And there's specialized software that you can use to recover that file. So if you have a phone and you want to sell it, and you just do a system restore, and you go sell it, they can still retrieve your data. So there's what we call destructive delete. So that destructive delete will go into every compartment of your storage and rewrite data on it. And it can take as long as 2, 3, 4 hours, depending on how big your drive is. Yes. Very, very simple. If I have a list now, right? You can see on this My File Manager, what does it say here? It says there are 89 files, right? And it tells me the complete size is 62 gig, right? So I want you to see what happens here. I'm going to look for that Legend of Zelda file that is very big. If I arrange by size, so it's 7 gig, right? So if I delete this, this should change from 62 to something larger, right? So check it out. I do that, it still remains 62. However, if I refresh this page, at some point, it will reflect that size. But it's reflecting that size based on calculating the valid files that are inside the index. So when it comes times to use that space, we don't have to erase to use it. Think of it this way. If I have a blackboard, let me reopen my OneNote. If I have a whiteboard or a blackboard like this, right? I can, for example, if this is my notebook, right? And I have these lines. These are my free space, right? So I can write whatever I want, write. So let's say I wrote a paragraph and I occupied some space. Deleting means coming in and removing each item so that it's gone forever. So I'm saying this is not how your computers work. How your computers work is if you write information for a particular file, there is also a table of content somewhere that says this file X is on page 2, for example. When you delete it, it is this entry that gets deleted, not the main one. So this space will be considered free space, even though the file is still there. So when it comes time to use it, what happens is you write on top of it. That's when you actually destroy it. But you don't actively delete it at the time you think you're deleting it, which means if you've not used that space, somebody else can still retrieve the data from that particular location. That's what that means. So the files, you have fields, you have records, you have directories, and you have folders. We've already explained all of this. The last thing we're going to be looking at here is this. The naming convention of these files are that you have the file name and a dot with the file extension. The file extension tells you the name of the file or the name of the program that created the file, sorry. So in other words, the dot so-and-so is basically who's your daddy, who produced you. In this case, this is a BAT file. A BAT file is a batch file, which means it's a program that you can execute. So if I go to my file manager, you can see the, let me undo the Legend of Zelda delete. You can see it's a .nsp. So NSP is the Nintendo Switch file type. So again, it's interesting. Let me just go ahead and show you. So there's for those of you that are not too into gaming, this is the Nintendo Switch. This is what it looks like. It's a game console. So this Switch runs a Linux operating system. So it runs games basically, and a game is just a program. That program is a file, and that file has an extension that defines its filing system. So the .nsp is a filing system that is for the Nintendo Switch. So if I try to open this file on this computer, look at what happens. I double click, it says there is no application set to open this document. You can either search the App Store to see if there is, or you can choose an application if you have one custom installed. Now, and of course, there's no software that will open this because it's not the right file system. In other words, my operating system cannot read this file type because it doesn't know, it doesn't understand it. So the file name includes basically the name of the file and the extension. So we call this the absolute file name. And we call the name and the address of where the file is the relative name. So the relative name includes the name of the file, the extension, and the address where it is stored. So here you can see in this example, C drive, Windows System 32, make a backup.dat. So this is the relative file path name. If I copy this file and move it to a different location, the address, the path will also change. That's why we call it relative. And that's that. Also, in a system, there is, you remember when we talked about security, who can access what file? You can see who can access a file by its access control matrix. So what's an access control matrix? It's a description of who has rights over a file. Let me show you an example here. So in this image, you can see the user is called Shum. Sorry, Shum at Sol. So at Sol is the name of the user. So Sol is the name of the user. So you have a bunch of files and directories here. The first character, so here you have the name of the files, right? The first character, the D, refers to the file type. D means directory. Then the next RWX, this R position refers to the user's permission. That is the logged in user. The second position, which is the, here you have blank, 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 but there are three positions here. RWX represents the user's permission. The next category represents the group's permission. And the next category represents the everyone's permission. And then you have the number of hard links. And here you have the owner's name. Here you have the group name. Here you have the size, the date, the time, and then the file name. So inside this folder, there is basically a directory called mail. This mail directory, we know it's a directory because of this D. And the user who owns this folder has read, write, and execute privileges. So these three positions represents to the permission. You can see them here. R means I can read the file. W means I can read and write the file. That means I can open it and change it. And then executable means I can, if it's a program, I can run it. So once these permissions are given, then I can operate it. So what are we talking about? Look at how we're talking about here. Here's user one. The file, for file one, he has RWED in his description. So what does this mean? RWED. Here's what it means. The first three digits are the user's permission. Then the user group's permission, then the public permission. In other words, I can be part of a group. What's your intake code? Your intake code, if you go to the attendance system, you will see is what? What's your intake code? Let me just open it for demonstration purposes. So if I open your app space and I go to the timetable, these are your intake codes, right? So in Appit server, all of you belong to one of these groups. This APD or APU, whatever you are, you belong to that group. So if a file is created on the computer server, on APU server, it will have your individual permission description and your group's permission. So everybody that belongs to that group will have that permission. And you specifically might have other permissions. So for example, I am part of your group, but I have more permission over some things than you do. So I inherit your group permission, but I have my extra permission. So that's what this is showing here. So let me show you a real life example. I've opened up my terminal here. So let me clear my screen. I have here, I'm going to open up my list of devices, my list of files, and you can see here, I've listed out my files, and this is my same downloads folder. So inside my downloads folder, let me see if I can find The Legend of Zelda. That same file called The Legend of Zelda, and it's here. You can see it down here, The Legend of Zelda, NSP. So here, we can now look at the permission of the file. You see the first item here is a dash. A dash means it's a file, it's not a folder. If it's a D, it means it's a folder. So here you can see, let me go back to this diagram here. So the D means it's a folder. Next, where is it? I have to highlight it again. There we go. So over here, then it has RW. That's my permission. I can read and I can write. But you see the execute, it's dash. It means it's not a program file. It's not an executable file. Then for the group, it has read, but it doesn't have write. It means other users of my group on this computer cannot edit this file. And they cannot also execute it. And then the public, the file. So if I copy it on a pen drive and somebody else puts it on their computer, it has only read access. It cannot edit, cannot execute. You get it? And if you compare it to the other files that are inside here, so for example, here's an MP4 file. Is it an executable? No. Is it read? Yes. Can I write? Yes. Others can only read, can only read. So other users on this computer that are not me cannot edit this file and so on. You get it? So that's that about this guy. So here on this table is just showing you examples of the access control matrix for different users. So here you have user 1 all the way to user 5, and you have file 1 all the way to file 4. And you can see the different permissions given to each of these users. And the description is a dash means it's a file, a D means it's a directory or folder. R means read, W means write, X means executable. The first three refer to the individual user, the next three for the users group, and the next three is for the rest of the world, the public space. So this is how it's written. You can have, it's a sequence for the operating system, it's a sequence of zeros and ones. A 1 means true, a 0 means false. So if under read, I have a 1, it means, yes, this guy can read it. W1 means, yes, this guy can edit. X means 1, yes, this guy can execute. A 0 means no, they cannot read, or under W, they cannot edit, or X, they cannot execute. You get the idea? All right. So that's that about access control and the file management system. So to shorten it, it's written as basically it's written in hexadecimal value. So 111 is the first 3 digits. It's if you convert from binary to decimal, you get a 7. So 777 means everybody has read, write, and executable permission. 755 means the original user has all the privilege. They can read, they can write, they can execute. But for the other, they can only read, they can't edit, and they can execute. So this is a program that you can read and you can execute, but you can't edit. So for the other 2 users, you have 55. So it can also be 711. 711 means these guys can only execute. They cannot read. They cannot write it. They can only run the program. How is what possible? To read it means to open it for editing. So you cannot open or access the file, but you can run the code. Does that make sense? Okay. And I believe that's that. So you can see here, you can set the permissions by using the change mod command, but this will only work on Linux systems. On Windows systems, you can just do it by right-clicking on the file and changing the permissions manually there. So if you have a Windows system, you can actually just right-click on the file, go to properties of the file, and under tools, you can then begin to play around with some of the permissions. So you can actually create a file and make it read-only and share it with your friends, and they can open it, but they can't edit, they can't change anything. Yes, so this is the Linux terminal that shows you how to go about doing the change commands and so on. And that's that for file management. So what's the moral of the story? We just looked at what file management was, why it was important, and its primary functions. It's not something too important. The last thing we will be talking about is going to be the disk management. Now, the disk management is also very, very, very simple. How does it work? Well, here's how it works. With regards to disk management, instead of looking at the RAM now, we're looking at the storage device. How do we access data from the storage device? In other words, right now, if you look at my computer, there are multiple programs running. Each of these programs may require data access from my storage device. So how does my operating system manage my storage device to provide information when it is needed? That's what we're going to be looking at. So there are algorithms. So here I have multiple programs running, and these multiple programs will submit requests, just like customers at a restaurant will submit an order for what food they want. All these orders will go to the kitchen, and they have to be arranged, and we have to decide which order to do first. So in this case, if all of these programs submit a request for data on the hard drive, which one do we do first? That's what we're going to be looking at. How does the operating system manage the disk? So by the end, we should be able to explain the functions of a disk and the disk scheduling algorithms, and describe how the algorithms actually work. So similar to what we did in process control management, you have the first come, first serve, shortest seek time, scan, CLOOK, look, and CLOOK. And we're going to be explaining them. So first, we need to understand a couple of things. You have two primary types of devices, storage devices: sequential access, Chinese scroll, and direct access, SSDs or hard disk drives. When you want to open up a file, here in this example, I have my file explorer, right? I can select the file and I can double click on it to open it in a real program, and I can begin running the file. So here I can press play and I can begin running the file. So when I double clicked on the file, what actually happened? When I double clicked on the file's address was sent to the hard disk and a request was made. Copy this to RAM so that the CPU can fetch, decode, and execute it. That's why there's a little 1-2 second pause from when I double click it. So double clicking it is me sending the instruction, fetch this file. I am not running this file from my hard drive. I am fetching its data and putting it on RAM, and from RAM, it's going to my video card, and from my video card, it's going to my screen through the operation and instruction of my CPU. So because of that, if I was dealing with a sequential device, I will have to wait for that sequential device to rewind or fast forward to the correct location where the file is. It takes a long time. So as I'm operating, all processes are saying, I want this data. I want this data at this address. I want this data at this address. I want this data at this address. So there's a request queue. Just like when several people place an order in a restaurant, the orders are placed in a queue. And the kitchen now has to determine whose work gets done first. So there's sequential and there's direct access. Now, the way the disks is it's divided into sections. And these sections are called sectors. So you have a track. A track is just a lining of magnetic material. Those are the circles you see. They're made up of magnets. These magnets are broken down into subsections called sectors, and these sectors are broken down into subsections called blocks. So your hard disk drive reads data blocks from these sections. Your solid state drives also reads data blocks, but there's no read write head. It's a different mechanism. All I want you to understand from this slide, you don't need to go into the details of how to draw this and the names of the different parts. What you need to understand is your hard drive is a storage device. and it arranges information by compartmentalizing the content, just like you would a cupboard. So these blocks that you're seeing here, these boxes, are basically locations for where you can store your zeros and ones. That's all you need to understand. Now, if you are trying to receive data, retrieve data from a disk, you need to know the address of where that data is. So here you can see as an example in green is the location of a particular file. It's on a cluster of sectors. So that's for a particular file. So this is what it looks like in real life. Now, this is a hard disk drive. Most of your computers today use solid state drives, which it doesn't look like this anymore. So the hard disk drive and the solid state drives are all direct access devices for the most part. But even though they're direct access devices, if a list of requests comes, the operating system has to determine which request to handle first. And it decides this based on the algorithm. So for a disk scheduler, the operating system needs to operate as efficiently as possible. It wants to give fast access and increased bandwidth. Increased bandwidth means I can read or write many things at once, not just a little piece of data, a large amount of data. The access time is the time it takes for the hard disk or the hard drive to find the information you want and to copy it into memory so that you can begin to operate on it. So the disk bandwidth is calculated by the number of platters over the cylinder area that you're going to be covering. Now, I know I'm mentioning a lot of words that might not make immediate sense. This is because I'm skipping through this because this is now obsolete. Computers don't use disks. They use solid state drives now. So the technology is a little different. So I'll give you a link to a video later on. If you want to increase your knowledge on these technologies, you can watch it, but it's not necessary for exam, so you don't need to worry too much about it. What it is necessary for exam is to understand how disk scheduling works. So here you can see on a Windows system, when you receive a request, the Windows operating system has to determine how to fetch these files, because the way the files are arranged on your hard disk is not that everything is arranged in a nice, neat little single position. You can see here that there are lots of fragments of files. The gray areas are the free space. The red areas are fragments. That is space that is too small to be useful, just like we mentioned early on. The blue are defragmented. Those are contiguous spaces. And then the green is the allocated where files are actually stored. The yellow is the MFT, which is basically a header for the hard drive to use to store particular kind of information. And the dark yellow are being processed. Those are areas that are currently being written by a file or being read by a particular file. So this, if you were to now talk to this hard drive and say, hey, I want to copy a file from this location to another location, then it will put it in a service queue. And that service queue is operated by an algorithm, which then decides later on, all right, this is what we're going to do. So the techniques that can be used for scheduling the read or write activities are as follows. So let's start with the first come, first serve. It's the simplest, it's fair, and it does not provide the fastest service. So requests are handled as the requests come. First come, first serve. So if I have a queue, the first item on the list is the first item I fetch. Now, in order for this to make sense, I want you to imagine this scenario. You are a library clerk and you're sitting at the front desk. 3 students come to you. One student says, I need a book on engineering. They give you the name. The second guy says, I need a book on computer science. You take the name. The third guy says, I need a book on business, and you take the name. You have 3 requests that require you to go to 3 different sections of the library. How do you plan your route? How you plan your route will determine how long it takes you to retrieve these items. One clerk can say, all right, the first request is the engineering book. So they will go all the way into the library, pick up the engineering book, and come back out and give it. Then go to the next request. The next request is computer science book. Then go back in again to the computer section and then bring it out. Then the third request is the business. Then go in and come out. That's clerk number 1. Clerk number 2 says, you know what? The first book is further away. The second book is right at the front, and the third book is right here. So instead of me to go one by one and come back, why don't I just go pick this one, pick book 1, then pick book 2, then pick book 3, and then come back? So the first book was engineering, so I go to engineering, pick it up. Before I come back from engineering, I go to computer science, pick it up. Then from computer science, go to business, pick it up. Then a third guy says, you know what? Instead of going by order, first come, first serve, I will go in a straight line. I'll plot my travel such that it's a straight line. Allow me to demonstrate using a diagram so that it makes more sense. So let me open up my OneNote. So I want you to imagine this is the library, right? So this is my library. So the clerk is right here. This is the entrance. So let's say the computer science section is here. The engineering section is here. And the business section is here. And the request is engineering, computer science, and business. This is the entrance. And the pathway is like this. So there's a pathway where you can go to the computer science. This is the road. So you can follow any of these pathways to go to anywhere. So what we're saying is clerk A, that's the first guy, he goes one by one. So he makes request 1, then he goes and does request 2, then he goes and does request 3. Clerk B, what he does is he does request 1, then he goes to 2, then he goes to 3, all in one travel. So that means if I was going to give an example, let's say this is the clerk. This circle represents the clerk. The clerk, I have to highlight this. Sometimes the program crashes, so I have to close this and reopen it. There we go. So I have to redraw this. There we go. So the guy has to come this way. This is the pathway, as we mentioned. So clerk A, we said, does request 1, then 2, then 3. Clerk B does 1, then on the same run does 2, then on the same run does 3. Right? So this way, it's like this now. It's like the clerk comes, for clerk A, he goes all the way to engineering, and then he comes back. Then he goes to computer science, then comes back. Then he goes to business, and then comes back. You see how long it takes. For guy B, he says, all right, the first request is engineering. So he goes to engineering, picks it up, and then goes to computer science, pick it up, and then goes to business, picks it up, and then comes back. Clerk B can say, instead of going to engineering and picking up and holding the book and moving along with the book, guy C might say, all right, first I will go. Guy C will say, first I will go to the business, pick it up, then computer science, pick it up, and on my way back, pick up the engineering book and then come back. Which one do you think is more efficient? So guy C says, I'll go to request 3 first, then request 2, then request 1. Obviously, guy C has a better technique. And that's what we're going to be looking at, the technique. So for first come, first serve, here's how the disk is represented. Here you can see the disk has several sections from section 0 to section 199. This is a graph down here. It's actually a graph. You just need to understand that the sectors of the disk are from 0 to 199. Right now, the disk read-write head is at position 53. That's this dot here, the first dot. So whilst the read-write head, the clerk, is on position 53, this is the request queue. We want sector 98, sector 183, then sector 37, then sector 122, and so on. This is the request queue. So the first come, first serve says the first come is sector 98. So it means from sector 53, we have to travel to sector 98. The distance between 53 and 98 is given by 98 minus 53. That's how many sectors we have to travel. And knowing the number of sectors we've traveled, we can calculate the time we've spent traveling. Just like we can calculate the time it takes the clerk to get to the engineering versus the computer versus the business sections. So if we have an algorithm, we want to calculate how many movements we've done to calculate the total time it takes us to actually finish the request. So in this case, since we're starting with 98 from position 53, from 53 we go to 98. After 98, we want sector 183. So from 98, we go to 183. And then we want to go to 37. So from 183, we go to 37. From 37, 122. From 122 to 14. From 14 to 124. From 124 to 65. From 65 to 67. Does that make sense? The movement. So what this means now is if I wanted to, say, calculate the movements, I can take this queue, right? I can take this and I'm going to bring this image into my OneNote. So let me just find some free space here. So what this means is if I want to calculate the number of disk movements, I will start by looking at the first position, right? The first transition we did was here from 53 to 98. So I will say, what is 53 minus 98? Now this is going to give me a negative number. But I'm not interested in positive or negative numbers because I know I just want the distance. So it's always going to be a positive number. So I do the absolute value. Do you guys in math remember this? The absolute value means the positive value. So I'll calculate 53 minus 98, or rather 98 minus 53. Then I will look at the second transition, which is 183. So I will add the number of head movements to now be from 98 to 183. Then I will also add that to the absolute value of 183 minus 37. Then I'll add that to 37 minus 122. Then I will add that to the absolute value of 122 minus 14. Then I'll add that again to the absolute value of 14 minus 124. And I'll add that to the absolute value of 124 to 65. 124 minus 65 and 65 minus 67. So that will give me a total of head movements of 640 after I do the calculation. So for this first come first serve technique, the disk needs to make 670 movements. Sector movement, it has to change. So if each sector takes 1 second, it means 640 seconds are spent. Using the same request, what if I use the shortest seek time first? Here's how that technique works. Rather than going first come first serve, since the head is at 53, it calculates which is the closest to 53. So if you look at this number here, what is the closest to 53? The closest to 53 is actually 65. So it starts by going to 65. And then from 65, which is the closest from the list? 67. And then from 67, which is the closest from the list? Is it 98 or is it 14? You can calculate, you'll find out it's, sorry, is it 98 or 37? It's 37. Then from 37, is the next closest 14 or 98? It's 14. Then from 14, the next closest is 98, then 122, then 124, then 183. From each position, it calculates from the list which is closest to me. Does that make sense, people? So the shortest seek time first, look at the path it travels. After you calculate from 640 sector movements, we have 236. That's less than a third, right? About a third. So we reduce the time spent reading or writing by 3. We reduce it almost by 3. Is this clear to everyone? People. Okay. It's coming out in the exam, by the way. So the scan technique, on the other hand, it operates very interestingly. The disk, once it starts moving, it moves in one direction and it only reads in one direction. What does it look like? Look at what it looks like here. When you do a scan, right? If the head is moving backwards or forwards, in this case, the head is moving backwards, right? And it's only operating in one specific direction at a time. So if the head was moving backwards at the point where it was on 53, and this request is received, on our path moving backwards, we need to figure out which of the sectors have data so that we can stop and pick up, stop and pick up, stop and pick up. So we move back till we get to the 0 point, and then we start moving forward again. And if there's anything on the way, pick up, 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 pick up. Does that make sense? So we're moving backwards and forwards, backwards and forwards. So whenever there's a request, if it's on our way, we just pick it up. That's all. We're just moving back, pick up. So the question can say we're moving in the forward direction. So if we're moving in the forward direction, we'll pick up, pick up, pick up, pick up. Then start moving back. If there's anything on the backward direction, also pick up, pick up, pick up, pick up. So we can now calculate based on this, how many sector movements? 252, as compared to the previous 236 for the shortest seek time first. So these are the three first, the first come, first serve, shortest seek time, and scan. Now, there's also another technique that is meant to improve the others a little bit. And these techniques are the C-scan, the look, and the C-look. So here's the C-scan. How does it work? The C-scan is the same as the scan, but it only takes data in one direction. So you notice here, it's moving, it only picks up information in the forward movement. So as we're moving forward, pick up, pick up, pick up, pick up, pick up, pick up, get to the end of the disk. On our way back, we don't pick anything up. That's the difference between the scan and the C-scan. The scan, back and forth, it picks things up. The C-scan only picks stuff up on the forward movement. So in our library example here, that's like basically saying this. For one example, we are moving for the first come, first serve. We go to engineering, then we go to computer science, then we go to business, then we come back. That's first come, first serve. For the shortest first, we're operating here, which is the closest? Engineering. From engineering, computing. From computing, business. So in this example, first come, first serve and shortest job first are identical. The scan is as we're moving in, we pick up engineering, we pick up computer, we pick up business, also identical. I want you to imagine a scenario now. Let me change this a little bit so that it looks more interesting. Let's say business is not here. Let's say business is actually here. And engineering is here. And the list is engineering, computer science, and business. So in this case, our first come, first serve will operate like this. We will go to engineering first, then computer science, then business, then come back. For shortest job, shortest seek time first, We will go to business first, pick up, go to computer, pick up, go to engineering, pick up, and then come back. And for scan, we just go as we're going on the way, we're picking things up. So we pick up from bus, computer, and then come back. For C-scan, you go, but you only pick up on your way back. So for C-scan, we don't pick up the business, we don't pick up the computer, we go to the end, which is the engineering, and we pick up engineering, pick up computer, pick up bus on our way back. So we go in, and on our way back, we pick things up. That's the C-scan. That's what's happening here. Here we're on our way back. Pick up, pick up, pick up, pick up, pick up, go back in, pick up, pick up, pick up, pick up. You get it? So that's your C-scan. Then you have your look. The difference between the scan and the look is, if you notice the scan, it scans from the 0 sector all the way to the 199 sector and back again. But if you look at our request queue, the lowest request we have is 14. And the highest request we have is 122. So there's no need for the read-write head to travel all the way to the ends of the disk. It's a waste of time. It's like there's a shelf, there are 10 shelves. I've sent you to go pick up something on shelf number 4, but you walk all the way to shelf number 10, and on your way back, you pick up something on 4. It doesn't make sense, right? So the response to that is the look. So the way the look works is it goes to the highest and the lowest sectors that are on the list. The lowest sector here being 14 and the highest sector being 124. And then it operates like the scan. So we start at position 53. So the look, it goes to the lowest position, then goes to the highest position, and then we calculate the number of sectors. Does that make sense? The C look is the same as the C scan, except it doesn't go to the ends. So how does it work? One direction only. When we're going, we pick up. Then we zip back to the lowest position, and then we proceed forward. So we calculate all the head movements, as you can see here, and we have a total of 322. Very simple. And that concludes the module. So any questions, people? I know we went a little over time. Good. So the last piece of advice. What is relevant for the test? We will cover that in a minute. But as a summary, this is what we have so far. So we've completed the disk management and the file management. So in the next short briefing that I'm going to give, I'm going to explain the important areas for the assignment, for the examination, for the last test, the test 2. So first and foremost, I want you to understand that the entire module tries to expose you to the architecture of the hardware of a computer system and the architecture of the software of a computer system, hardware, software. Under the hardware, we looked at several components, the input devices, the output devices, the processing devices, the storage, and the communication devices. And on the software bit, we looked at the system software, also known as the operating system, and the application software. This is the fundamentals of the module. So if you look at this document called your module descriptor, let me open up the module descriptor real quick. On your module descriptor, it outlines all the sections or the topics that we need to cover. So these are what we've covered so far up until number 9. We've covered everything in lectures. You will notice that in the case studies, these are practical exercises. How to build a computer system, how to evaluate a simple computer design, and your modern operating systems and virtual machines. So I explained to you that evaluating a simple computer design is in part done in your assignment. Building of a computer system and evaluating is in part done in your assignment. You were asked to evaluate the implementation of AI in logistics for a particular company that was running basically computer technology. This case study is supposed to have allowed us to build a computer system from scratch. But because of the holidays that we were having that were interfering with our semester, I think about 5 of our classes were interfered with, if I'm not mistaken, 4 or 5. So because of that, these case studies are going to be given to you in video. They're general knowledge things that you require for some of the courses that you're going to do in your second semester and in your level 2. So for the building of a computer system, I'm just going to teach you how to configure a desktop computer system, how to select the components for specific functionality and then implement. So from the selection of hardware components to selection of the operating system to configuring it for first-time use. It's going to be a short video. For evaluating a a simple computer's design, these 2 case studies go hand in hand. We will have a use case. We want to build a gaming device, or we want to build a media center. Here's how we select the hardware. Here's how we configure it and construct it. Then install the operating system, and then get it ready for first-time use. From A to Z. So that's the 2 case studies. In doing that, we will cover, of course, modern operating system because we have to select an operating system for our use case. And the virtual machines are basically a software that allows us to run other operating systems on our computer. So, for example, I have a virtual machine software called Parallels, and it allows me to install both Linux and Windows on my Apple computer, and I'm going to launch them both for you to see. So here you can see my Windows installation. And it's booted and logged into Windows. And then over here, there we go. So this is my Linux Fedora is also launching. And there it is. It's logged in. So this is a full-fledged Windows OS. Everything is there. So this is Windows 11. And here I have my Fedora. So you can see the application folder and whatnot. Everything is running. So right now on this machine, I have all 3 major operating systems essentially functioning. And they function buttery smooth. So here you can see. So this virtual machine just teaches you how to install the software, download the operating systems and install them, and you can practice with them. Just to get a taste and a feel. So that's basically it for the entire module. So let me go ahead and shut these off because they're consuming resources. I'm going to power this off. And I'm going to log out this guy also. Right. So what's coming out in the examination, in the test? The first test covered 1 to 4. The second test is just going to cover 4 to 8. 5 to 8, sorry. File systems that we just covered today. What am I going to ask you? Other than the objectives of file systems. There's nothing to, it's just conceptual knowledge. And I'm not going to ask you these conceptual things. So what you want to be very, very careful with are these algorithms. Your file management, your memory management algorithms and your disk scheduling algorithms and your CPU scheduling algorithms. Those are the most important bits. Everything is coming out, but all those calculations that we did are of specific importance. And what you covered also in your tutorial are of specific importance. So don't go into the test without knowing how to perform these calculations. The beauty of it is the calculations are very simple. If any of the calculations are confusing to you, you can look up YouTube videos that show how to break down in maybe simpler terms if you're still struggling with it. But for the most part, it should be easy. So the good news is test 2 is going to be much easier than test 1. Test 2 is going to be much easier than test 1 because test 1, those logic gate questions were a bit tricky to do. And then you had a lot of concepts to actually cover. But here you only have basically one topic, operating system. and the fundamental functions of the operating system, which are all these algorithms that you need to know. Mm. The other question, a lot of definitions that like define this, concepts. So everything here, yeah. But here you only have this one topic, operating systems. And we covered the whole topic yet again today. What's an operating system? A bunch of software that controls and coordinates all the activities of a computer. What are the categories of operating systems? They're this, and this. What are the types of operating systems? As examples, there's this, and this. What are the degrees of activities of an operating system? Interactive, batch, and interrupt, event-driven. What are the different functions or services provided by an operating system? Memory management, disk management, and process control management and scheduling. For scheduling and process control management, what are the algorithms? There's this. For memory management, what is partitioning? What is, what do you call it? The types of partitioning techniques, you know? Yeah. What is virtual memory? How is virtual memory implemented? Which is the paging, the concept of paging and segmentation. So for paging, there are algorithms, first come, first serve, least recently used, optimal, all of these things we covered it. They're all calculations. So they're very straightforward. Most of your questions here are going to be based on these calculations. So that's what you want to prepare for. No, it's just 5 to 8. So test 1 was 1 to 4. This is just 5 to 8. So like I said, I believe, but here's the thing. If you don't know how to perform these calculations, there's nothing for you to write. So it's either you're going to do very well or you're going to do very terribly. But you know what's coming out. There's no surprise here. It's one topic. The one topic is operating system, and it contains a bunch of subsections. So let me open up the chat area here to see if there are any questions. It's still going to be 1 hour. So this 1 hour is more than enough time for you. Believe me, most of you will probably be done in 30 minutes. Everything is multiple choice questions. Then we have chapter 5 to 8 only. Yes. How many questions is it? I think there are about 27 questions. These 27 questions, some of them are calculations and some of them are just select from the options given. So some questions you can finish as little as 20 seconds. Some will require maybe you sit down 5-10 minutes to perform a calculation. The definition and all the details should appear in chapters. Yes. The slides I can see only stop at chapter 6. Yes, the slides that I did today, I'm going to upload them after this class. So they're just going to be 3 sets of slides for file management and 2 for disk scheduling that I just used now. So I'll share that with you right now. Could you change the timing because we have to pray? So yes, with regards to this request, remember the exam hall is being used by the entire university. So when I requested for space at the exam hall, they give me the space based on availability. So what I've decided to do is the test is 1 hour and I have booked the venue from 2 to 4. So normally your classes resume at 2:30, right? So for those going to Friday prayer, you can resume at 2:30 and come and still have enough time to do the test because it's just a 1 hour test. So if you come in by 2:30, you find yourself to the exam hall and you sit, you get comfortable, you sit down, you have, let's say by 2:40, you started your paper, you should be done by 3:40, which there's still a little 20-minute window. So, but try your best to be here as early as possible because you will be taking attendance. So I'm not saying the test starts at 2:30. I'm saying everybody else needs to be there by 2. So if you're not going for Friday prayer, still come by 2 because there's going to be a long queue where you're going to have to sign your attendance. And remember, there are 400 of you. So even if everybody comes at 2, you won't be done entering the hall till around 2:30. And the test is designed to be open and you can start. And when you open and start, you will have exactly 1 hour to finish. So depending on when you start, you have that 1 hour. So keep that in mind. It's not a 2-hour test, it's a 1-hour test, but we have a 2-hour period to do it. Can you delay till 3 p.m.? Again, I cannot, because you will only have 1 hour and it's going to be from 2 to 4. That's what we got booking for. Anything after that, the hall is going to be in use by another group. So if I can, I will talk to them and see what we can do, then make an announcement. But if I don't make an announcement, just get ready from 2 to 4. Is the paper given for calculation? Yes, you can request for paper if you want at the exam hall. Later, could you show us the code? Yes, I'll show you the attendance code, no problem. Can you enable the option where we can skip a question and maybe come back? No, I won't be doing this because it prevents cheating and sharing of answers. So I won't be doing that. It's if you see the question, if you know it, you answer. If you don't know it, you move on. So I cannot do this because it's a precaution against cheating. So if there are any other questions, you can go ahead and ask. Yes? It will calculate. So you just take all the Q in the list. So he's asking for shortest seek time first, right? Let me just show you with a diagram. Where is it? For shortest seek time first. What happens is from any position you are, you look at the queue, this queue. So let's say I'm on 53 right now. That's the beginning. The head is at 53. It says that in the question, right? So from 53, I'll calculate 53 to 98, 53 to 183, 53 to 37, everything to see which one is closest. Yes. So his question is, what if I go through this entire queue and there are 2 requests that are on opposite sides, but the same movement of head? In that case, I implement first come, first serve. So the first that appears in the queue is the one that I go for. So where you have 2 separate sectors that are equidistant in the opposite direction from a request, you go with the first one that appeared on the request. Yes, I would upload the slides after the class. Yes. I think because the time is way up, and God knows I cannot do the manual one. Can I change this? Okay, what you do is just write your name down here. I'll come and update. So for those who are late, just say attendance. Just type attendance. Your name will appear in the chat area and I'll refer to it later. For those who cannot scan, because the time for the scanner, and there are too many people absent. There are about 103 names, so I can't go through 103 names. So just write your names in the chat area. Just write attendance, and move on. As for the rest, if no questions, I think that we have come to the end of our semester. I will be uploading those videos that I mentioned for the case studies. So even during your holiday, it's an exercise that you can practice. So you can look at how you can turn your computer into a game station using RetroArch. I'll show you a couple of videos for that. You will also have a couple of videos for installing a Linux operating system using a virtual machine. If you're interested in practicing that, it's good to practice your programming in the Linux environment because it's an interesting operating system and it's much more fun. And remember, it's a free operating system that you can download and customize as you like. So by the time you resume in your second sem, you should be prepped and ready to handle it. The reason why we were unable to cover it is just because of the holidays clashing with our class periods. So with that said, I wish you all good luck and I'll see you around.